Alright, so for this section, 11.7, it's going to wrap us up on chapter 11, and we want to introduce our last new rule, and it is called the chain rule. And so first we're going to recap all of our derivative rules that we have thus far. Then we're going to talk about a composite function and what that is, and then we'll talk about how the chain rule applies to composite functions with derivatives. Okay, so thus far we have three main derivative rules. We have the power rule, which was our base rule that kind of allowed us to do everything that we needed to do with derivatives. And it was that f of x equals x to the n. Then f prime of x, we bring the power down, and then we subtract 1 from the previous power to make the new power. Then we have the product rule. The product rule is when we have two polynomials being multiplied together, say like u and v. Then the derivative is equal to the derivative of one times the other plus the derivative of the other times the one. And then lastly, we have the quotient rule. And the quotient rule is when we have a rational expression, so a polynomial being divided by a polynomial. And we conveniently called it low and high. So we have when high is divided by low, so high could be 2x plus 4, low could be 5x squared minus 6, or something like that. Then the derivative is low times the derivative of the high minus high times the derivative of the low all over low squared. Okay, so these are our three basic derivative rules that we have, and we're just going to introduce one more derivative rule. All right. So first, let's talk about a composite function. So if f and g are functions, then the composite function of f and g is represented by this notation, and we just read that as f composite g, which really just means that we're going to take whatever g is and plug it into f. Okay, so whatever function g is, we're just going to take that and plug it into f. Yeah. So looking at it, a couple examples here, let's look at number 1. So I have 8x plus 12 and 2x plus 3, and my goal is to find f composite g. So I'm going to take my g function and just replace x in f of x. So I have 8 times 2x plus 3 plus 12. Do some algebra here. Equals 16x plus 36. All right. And then doing the same thing in the other direction. So now I'm going to take my f function and just plug it in for x in g. So I have 2 times 8x plus 12 plus 3 is 16x plus 24 plus 3 is 16x plus 27. All right. And so now I want you to pause the video and try number 2. All right, so assuming you pause the video, so I'm going to come over here for number 2. And so I want to find f composite g of x. So I'm just going to take my g of x and just plug it into f. So I have 3 times x minus 4 squared minus 8 times x minus 4. Really, the only cleanup I need to worry about doing is this 8. Because after we learn the chain rule, you will find that it is easier to take the derivative of this than what it is to square that out and do the FOILing and all that, and then apply the power rule. All right, and so then to do the composite function in the other direction, I just take my f of x and I just plug it in wherever I have an x in g of x, and so I end up with 3x squared minus 8x minus 4. So that's how a composite function works. All right. And so now, when we have a composite function, which just means we have some kind of function inside a function, then we can apply what is called the chain rule. And the chain rule, you take the derivative of the outside function and you just carry over whatever the original inside function was, and then you multiply by the derivative of the inside. Okay, so let's look at how that works. So for the first one here, all right, we have y equals 4x plus 3 to the 5th. So what I would advise you to do, just to help yourself out, I would break this apart and go ahead and denote what your inside and outside function is. So my inside is 4x plus 3. My outside is just x to the 5th, because I just have the variable being raised to the 5th power. So now, according to my chain rule, I just do the derivative of the outside. So I would have y prime is equal to, so doing the power rule, bring my 5 out front, tag along whatever's inside, the 4th, and then I have to multiply it by my inside function, which is 4x plus 3, or the derivative of the inside function, and so that's 4. So my final answer is 24x plus 3 raised to the 4th power. Okay. I want to do the same with the next one. So this is 1. We'll say this is 2. But instead of having a square root, I want something being raised to a power. So I'm going to have 6 plus 3x squared to the 1/2. With my inside function being 6 plus 3x squared, my outside function being x to the 1/2. So I do the derivative, so I bring the power down, tag along the inside, subtract 1 from the power, and then I have to multiply by the derivative of the inside. Well, the inside is 6 plus 3x squared, so doing the power rule, I get 6x. So just to clean this up a little bit, I could rewrite this as 3x over 6 plus 3x squared to the 1/2 power. Okay. And then the last one that I want to talk about is 1 over 4x minus 1. I'm going to rewrite that so that I have 4x minus 1 to the negative 2nd power, because I can't do anything with that power in the denominator. So instead I just rewrite it to be negative 2. And then again, I just apply my chain rule. So I bring my negative 2 out front, copy the inside, and then I multiply by the derivative of the inside, which is 4. And so I end up with negative 8 over 4x minus 1 to the 3rd. Okay. All right. So this does conclude all of our calculus rules. Next, we will get into calculus applications in Chapter 12. Please, just if you have any questions, feel free to email me. And as always, have a great rest of your day.